Hey everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. Today we're going to be talking about Chapter 14, which is about redox reactions. This is a subject that's near and dear to my heart because I spent most of my PhD work thinking about redox reactions. And that was back in the day when I was in graduate school. I was still married to my first husband, and my last name was Totten. So you'll see that name pop up a few times as we go through this lecture. Before we get started with redox reactions, we're going to review some stuff about oxidation states. This is always good review because you forget this stuff from your Gen Chem class. So oxidation states, this is hexachloroethane. Oxidation state of chlorine, almost always -1, right? The chlorine in this has a -1 oxidation state. So all 6 of these chlorines have a -1 oxidation state. And that means that these two carbons must both have a +3 oxidation state. I'm not doing this. I'm trying to draw with my mouse. It's pretty bad. But anyway, +3 oxidation state. And so over here, we have 2 chlorides that have been lost. And of course, they clearly have a -1 oxidation state each. Each of these chlorines is still -1. And so each of these carbons is +2. 2. Oh, bad. That's a 2. I know it doesn't look like it. Okay. So what's happened here is carbon has gone from a +3 oxidation state to a +2 oxidation state, which means that carbon has been reduced because its oxidation state went down. And in order for that to happen, some electrons had to be donated. 2 electrons here, 1 for each of these carbons. And in any balanced redox reaction, in any reaction, in any balanced reaction, the charges have to balance. So we have a -2 charge here and a -2 charge over here, and that's what makes the equation balanced. Where do those 2 electrons come from? Well, that's a long story that we'll talk about a lot as we go through this lecture. Next reaction, pH stands for a phenyl group or a benzene ring. And so this is a nitrobenzene, and it gets reduced down to aniline, so NH2 on a benzene ring, that's aniline. So again, these oxygens are -2. Oxygen is almost always -2 oxidation state, and there's 2 of them, so that makes -4. So this nitrogen must have a +4 oxidation state. Over here, these hydrogens are both +1. Hydrogen is almost always +1. And so there's 2 of them, so that means that this nitrogen must have a -2 oxidation state. So it's gone from +4 to -2, took 6 electrons to get there. To balance out the charge and everything else, you have to add these protons. This is a common reaction in groundwater. Nitrobenzenes are common groundwater contaminants, very common industrial chemicals. And in the groundwater, they can be converted from nitrobenzenes down to anilines. In fact, this was happening in the groundwater at Chambers Works, which is that site on the Delaware River that was owned by DuPont. And at that particular site, we used the ratio of aniline to nitrobenzene as an indicator of the redox status of the groundwater. So that was kind of a cool thing to do. Then here, next equation, we have sulfate being reduced down to sulfide. This happens in seawater, especially in estuaries where you have some brackish water, and you've got salt marshes where there's anaerobic conditions in the sediment. So sulfate here, all these oxygens have a -2 oxidation state, right? And there's 4 of them, so that's -8. And then 2 of those charges are right here. So the sulfur molecule here, sulfur atom, has a +6 oxidation state. +6. It's ugly, but +6. And then over here, again, the hydrogen is +1. And there's a -1 charge here, so sulfur must be in a -2 oxidation state to get that to work out. So you go from +6 to -2. It took you 8 electrons to get there. Again, this is common reaction in sewers. This hydrogen sulfide smells bad, and that's what gives sewers and other anaerobic conditions their bad smell. Hydrogen sulfide is also quite toxic, so at higher concentrations it can be really deadly. Next equation is carbon dioxide being reduced down to, this is a molecule of sugar, C6H12O6. We're using this as sort of a proxy for all the reduced carbon in the world, all the natural organic matter. So again, oxygen -2, and there's 2 of them, so this carbon must be in a +4 oxidation state. Here we have, again, -2 for the oxygen, times 6 oxygens gives us -12 here. Hydrogen is +1, and there's 12 of them, so that's +12. So -12 and +12, that means that carbon has an oxidation state of 0. So oxygen is being reduced from +4 to 0. That takes 4 electrons, and there's 6 of these carbons here to get the oxygens to balance out. 6 times 4 is 24 electrons changing hands. Next reaction, oxygen in its molecular state has an oxidation state of 0, and then oxygen over here is -2. And there's 2 of them, right? 2 of them. So that's -4, which means it took us 4 electrons to get there. This thing, the P, stands for porphyrin, which is this structure right here. This is the kind of thing that you find in living things, bacteria and plants and stuff. And when they die, they let loose these porphyrins, and they are great chelators of metals. So here's an example. Iron is shown in the middle here. Each of these nitrogens is donating that lone pair of electrons toward the iron here to chelate it, and that changes its redox potential. So iron can always cycle back and forth between a +2 and a +3 oxidation state. The +3 iron is not very soluble, so it will very quickly precipitate as a mineral unless it is chelated by this porphyrin. So the porphyrin keeps the iron soluble and also changes the redox potential of this reaction. So to go from +3 to +2, we must have added 1 electron. This thing is called a quinone. I'm going to attempt to write the word quinone here with my crappy pointer. And quinones are, again, part of natural organic matter. You'll find these in all the decaying natural organic matter in the world. They'll have different R groups off of here, but these quinone functional groups are quite common. So if you add the 2 hydrogens, you have to add 2 electrons to make this work out. So you're reducing the quinone down to this thing, which is called a hydroxyquinone. It takes 2 electrons to get there, and because these functional groups are part of natural organic matter, they act as electron shuttles that move electrons around through the environment. So they're important. We're going to talk about them some more. All right, so we're going to talk about a bunch of different types of redox reactions. And these redox reactions can be abiotic, meaning that there's no biology involved, or they can be biological. Now, most of the cool and interesting redox reactions that we care about as environmental chemists are biological. Bacteria are the world's greatest chemists. They can do amazing, amazing things. But there are a few things that are abiotic. Now, the word abiotic can be a little bit difficult to define, and we're going to define it here as meaning that the reaction does not involve a living organism. It could be that the organism died and released those iron porphyrins or those quinones or something, and those are playing a role in the reaction. But as long as you don't need a living organism to make it happen, we're going to quantify that as an abiotic reaction. So here's some examples. AR is what they're using for the phenyl group. I was using pH, but anyway, this is a benzene ring with a nitro group on it. Can be reduced to aniline, as we discussed. To get there, you need some electrons. Where do those electrons come from? Well, they can come from those iron 2 porphyrins. So iron 2 is up here, being shuttled between iron 3 and iron 2. They can also come from these quinones. So they act as electron shuttles. They donate their electrons over here to reduce organic pollutants. And then where do they get theirs from? Well, they get them from some bulk electron donor. Could be hydrogen sulfide, could be iron sulfide species, could be reduced carbon. They put the CH2O in brackets here. If you multiply that by 6, you get C6H12O6, which is glucose. So this is just their proxy for reduced organic carbon. Could be hydrogen, which is present in anaerobic systems. And so these act as the bulk electron donors. They give their electrons to these electron shuttles, which then hand them off to the organic pollutants. So this is the kind of thing that happens pretty frequently in environmental systems. And again, these types of reactions would be considered abiotic because they don't involve a living thing. There might be living things, living organisms doing the bulk electron donating, but this step is considered abiotic. Okay? So again, the dividing line between what's abiotic and what's biotic can be a little tricky sometimes, but this particular type of reaction would be considered abiotic. So here's some examples of common environmental redox reactions. Here's a carboxylic acid. It's being reduced down to an aldehyde. Okay, actually this, you see the arrow is pointing to the left, meaning that this reaction in the environment typically would go the other way. The aldehyde would be oxidized to a carboxylic acid. But you remember from Gen Chem that the way we write redox reactions by convention is that we always draw the electrons on the left-hand side. So we draw it this way, even though most of the reaction in the real world will be going the other direction. Here's our quinone to hydroxyquinone. This goes back and forth pretty readily. That's why there's a two-headed arrow here. Here's an alkyl halide. So X is a halogen, a chlorine, a bromine, an iodide, bonded to a carbon. If you add 2 electrons and a proton, you can release that halogen as a halide, chloride, bromide, whatever, and replace it with a hydrogen. Okay, so that's a process that we call reductive dehalogenation. It's reductive because you need 2 electrons to make it happen. It's dehalogenation because you're removing the halogen from the backbone. Here's another example of reductive dehalogenation. We donate 2 electrons. We get to pop off both of these halogens, and we end up with a double bond here. Here's another example where you take 2 of these alkyl halides, and you can actually couple them, and they can start to polymerize. That's not so common, but it does happen sometimes. So this is all involves changes in the oxidation state of the carbon atoms. So this is all changes in oxidation state of carbon. The other mineral or the other element that undergoes lots of redox in the environment is nitrogen. So here's the nitrobenzene example that we saw before, nitrobenzene being reduced down to an aniline. I don't remember what you call this thing, but with the nitrogen double bonds, that can get reduced and then reduced further down to aniline. These structural features are very common in pigments and dyes because these long conjugated pi systems, this pi system is conjugated all the way throughout this ring and across the nitrogens because they all have sp3 hybridized orbitals going on. And when you have these long conjugated pi systems, that means that they absorb light, and that causes them to have a color, a pigment. So in dye and pigment manufacturing facilities, you're going to see these kinds of moieties, and then they can undergo interesting redox chemistry. And whenever you have reduction reactions, usually that means that there's no oxygen around, because if there was oxygen around, you'd be oxidizing. To be reducing, you have to have no oxygen, and so that's usually groundwater and sediments and sewers and places like that. And then the last element that often undergoes redox is sulfur. So here's a sulfur bridge. It can get reduced and broken apart. And then these sulfhydroxy things, sulfoxy, I don't know what you call this thing. It can get reduced down to a sulfide. So sulfur has lots of redox chemistry too. Recall from your Gen Chem that there's this thing called the Nernst equation where there's an electrode potential of a reaction. And the electrode potential is related to the delta G of the reaction. Its delta G is equal to N, which is the number of electrons changing hands, times F, which is Faraday's constant, times E, which is the redox potential. And that's expressed in volts or millivolts. So the whole point of E is just a replacement for delta G. And you're asking, well, why did we need a replacement for delta G? I was perfectly happy with delta G. I understood that. But E is what you get when you stick an electrode in something. And so when you stick an electrode in there, you measure some redox potential in millivolts, and then you need a way to relate that back to the delta G of the reaction. So E, the electrode potential of the reaction, is equal to E naught, which is like delta G naught. It's the delta G, the free energy change of the reaction when there's everything is at its reference state, so 1 molar of everything, 25 degrees C and everything else, plus RT divided by N times F. Again, N is the number of electrons changing hands, and F is the Faraday's constant, times the natural log. And then Now, usually we would think of this as products over reactants, but because we have this convention of always writing the electrons on the left side of the equation, the products are always going to be the oxidized products, and the reactants are always going to be the reduced reactants, and so it's oxidized form divided by reduced form. So the point of all of this is that if you stick an electrode in some solution where there's a redox reaction happening, you'll be able to measure an electrode potential. So for example, if you have your iron porphyrin going from iron 2 to iron 3 porphyrin, that has an electrode potential of minus 0.07 volts. I haven't explicitly written the volts out, but those are volts. And so we can couple this what we call a half reaction. And here I have broken with convention, and I put the electrons on the right side because I'm going to couple it with one of these reactions down here where the electrons are on the left. Okay, so if this is the reductant, the iron porphyrin is the reductant. If the oxidant is carbon tetrachloride, add an electron to it, you get the trichloromethyl radical and a chloride, and the E of this is 0.09. So if I add the minus 0.07 to the plus 0.09, I get plus 0.02, and as long as E is positive, it's favorable. Because remember, E is the negative of delta G. So delta G being negative is favorable, but for E being positive is favorable. So if I couple this reaction with this reaction, I add these two redox potentials, I get plus 0.02 volts, and that's favorable, and that is a spontaneous reaction that can go forward. But if instead I try to couple it with chloroform being reduced down to dichloro radical, again this is a radical, that has a redox potential of minus 0.19 volts, so I add minus 0.19 to minus 0.07, I get minus 0.26, that's not favorable. That's not going to happen, that's not going to be a spontaneous reaction, it's not going to go forward. So all I have to do is compare the redox potentials of the two half reactions. I can add and subtract them to figure out whether the overall redox potential of the combined two half reactions, the whole reaction, is favorable. So here's some examples of redox potentials of various things. And these are listed in order. So this is the delta E, or excuse me, the E, the electrode potential, but that's under standard conditions. And that would be like 1 molar protons, which is, a pH of 0, and that's not realistic. So here we've also given you E, what they call EW here, the W in parentheses. That is the electrode potential at pH of 7. Okay, so we really don't want to pay any attention to this column. This is not very helpful for us. We're going to pay attention to this column, and you can see that it's oriented with the most favorable reaction at the top and the least favorable reaction at the bottom. And what you see is that one of the most favorable reactions is reduction of oxygen. Oxygen loves to take on electrons and form water. This is a very, very favorable reaction because, again, the oxidation state of oxygen over here is 0. The oxidation state of water of oxygen in the water molecule is -2. Oxygen is very electronegative. It wants to be reduced. So this is a very favorable reaction. And so this is why, this right here is why humans breathe oxygen. Because it's a very, very good, very thermodynamically favorable electron acceptor. Because it has a very favorable redox potential. That's in the gaseous form, like when you breathe it. If you were a water-breathing organism or a bacterium, you'd have oxygen in the aqueous phase, and it's not quite as favorable, but still among all the other possible electron acceptors, it's quite favorable. After that, you got nitrate is a pretty good electron acceptor, plus 0.74. Then you have manganese oxides are good electron acceptors. Then you got nitrate here, being reduced to nitrite. Up here, nitrate is being reduced all the way to nitrogen gas, but here it's just being reduced to nitrite. Still pretty favorable. Here, nitrate is being reduced to ammonia. Again, pretty favorable. Here's an iron 3, right? Because each of these oxygens is -2, and the proton is +1. So this OOH has a net charge of -3, which means that iron must be a +3 iron. And over here, CO3 has a minus, we're used to seeing it as CO3 2-. So this whole thing has a -2. So the iron here has a +2 charge. So iron is being reduced. It's now got a slightly negative E, but if you couple it with a favorable reaction on the other end, you could still get a favorable overall reaction. Then you got pyruvate being converted to lactate. This is fermentation. Okay, so that's a reasonably favorable reaction. Then you have carbonate being reduced to methane. CO2 being reduced to methane, that's less favorable. Then you got sulfate being reduced here, less and less favorable as we go down the charts. And then down here we have CO2 being converted into glucose. So the point of this table is that the things at the top are the best, most favorable electron acceptors. And all living things need an electron acceptor and an electron donor. For most living things, the electron donor is reduced carbon. It's food, it's hamburgers and hot dogs, right? And so we as human beings get our electrons from food, and then we have to give the electrons away somewhere to some electron acceptor, and we use oxygen because it's very, very favorable. But not all bacteria can do that. Some bacteria are buried in sediments and sewers and the rumen of cows and places like that where there's no oxygen available. So in the absence of oxygen, the next thing they go for is nitrates, and they become nitrogen reducers. They can use manganese, things like that. They can use iron. They can undergo fermentation. And then when you get down to the bottom, methanogenesis down here, these are the methanogenesis reactions that are really relevant to us. These reactions are the least favorable. So sulfate reducers are actually a little bit more favorable than methane, even though it's not quite drawn that way on this chart. So when bacteria are trying to attack and find the best electron acceptor they can get, they start with oxygen, then they go to nitrate, then they go to fermentation, iron reduction, then fermentation, then sulfate reduction, and then finally methanogenesis. And that's shown here as an example. So if you have a dump site where you have a waste plume coming out, and let's say your groundwater is flowing this direction, so your contaminants are flowing that direction, what happens is that the first thing to get consumed is the oxygen. The oxygen goes away really quickly. Then the next best electron acceptor is nitrate, so the nitrate gets consumed next. Then the best electron acceptor after that, after the nitrate is gone, is the sulfate, so that'll go away. And concomitantly, as the sulfate goes away, the sulfide appears. And then finally, when there's nothing else, no other good electron acceptors around, bacteria will start to do methanogenesis. Now, different species do different things. Things that can do methanogenesis probably can't do some of these other processes. But some things, like especially sulfate-reducing organisms, can often use other electron acceptors. Maybe not oxygen, but other things. So this is a really common pattern that you will see in groundwater. So I mentioned that project that we were doing at Chambers Works. One of the things that they did was they did stick an electrode into the groundwater to measure PE, and they also measured dissolved oxygen. But those electrode methods are easy because you just stick an electrode in, but it turns out they're really not very reliable, because as soon as you pump the groundwater up out of the ground, it's in contact with air, it starts to absorb oxygen, it starts to oxidize, and crazy stuff starts to happen. So measuring PE is actually quite difficult, and it's really not a very good way to understand the redox conditions in the subsurface. So instead, people will look at things like the presence or absence of nitrate, presence or absence of sulfate and sulfide, presence of methane, and to some extent presence of oxygen, and use those as indicators of redox. And as I mentioned, we in the Chambers Works project, we actually use the amount of aniline relative to the amount of nitrobenzene as an indicator of the redox status. So these have different names. Aerobic respiration is when you're using oxygen. Denitrification is when you're using nitrate. Sulfate reduction is when you're using sulfate. And methanogenesis is when you're using CO2 and reducing it down to methane. Redox potentials. So you can couple any of these processes, any of these electron accepting processes with some other processes. So here's hexachloroethane. It's one of the examples I showed. Hexachloroethane taking up 2 electrons has, again, here's the EW value. That's the one we really want to look at, is this one. Has a really positive 1 plus 1.13 volt electrode potentials. That's a very favorable reaction, which means that this is a good electron acceptor, right? Compared to some of the other things we saw in this table, it's actually a better electron acceptor even than oxygen, although you certainly don't want to be breathing hexachloroethane. For bacteria in the subsurface, they might say, wow, that's a pretty darn good electron acceptor. I'm going to use that. Here's carbon tetrabromide, carbon tetrachloride, tribromomethane, which is a trihalomethane, which counts under our disinfection byproducts. Trihalomethane, that's also, these are all really favorable redox potentials. Here's perchloroethylene being reduced to trichloroethylene, quite a favorable redox potential. So where you have groundwater that's contaminated with PCE and TCE, it makes sense that bacteria would say, wow, this PCE is some pretty good electron accepting stuff. I'm going to use that because there's no oxygen around. I'll use these chlorinated compounds as my electron acceptors. Here's chloroform, again, a pretty favorable reaction. Chlorobenzenes, this is hexachlorobenzene to pentachlorobenzene, pretty favorable. In the groundwater at Chambers Works, there was evidence that chlorobenzene was being reduced down to benzene here, which is, again, it's a reasonably favorable reaction. Here's nitrobenzene going to aniline, favorable redox potential. Here's your porphyrin. Here's some of these sulfur-containing species, quite positive, and so on. And by the way, some of the redox potentials in this table came from a paper I wrote when I was a graduate student with my PhD advisor, Lynn Roberts. Okay, so what do we learn from this? Reductive dehalogenation is usually pretty favorable, and so bacteria will sometimes use these chlorinated and brominated species as their electron acceptors. The more halogens you have, the more favorable the redox potential is, going from carbon tetrachloride to, I guess, there's chloroform. Carbon tetrachloride to chloroform, you're going from plus 0.67 to 0.56. Going from carbon tetrabromide, 0.83, carbon tribromide, 0.61. So more chlorines or bromines, the more favorable the redox potential. And by the same token, bromine is a better compound. It has a more favorable redox potential than chlorine. So here's carbon tetrabromide plus 0.83, carbon tetrachloride plus 0.67. So bromine is easier to reduce than chlorine. Not shown on this table, but fluorine is then, by analogy, even more difficult to reduce than chlorine. So bromine is easier than chlorine. Chlorine is easier than fluorine. Aromatic halides are more difficult to degrade than the aliphatics. Aliphatics up here are the easiest, and then the vinyl halides, and then the aromatic halides are a little bit less favorable. So that's a good introduction, and that's where I'm going to end this lecture. Stay tuned to watch the next lecture, which will also be about redox.